In this video, we'll be having a look at a proof of Heron's formula in geometry. So if we have a triangle ABC where we label the sides BC as lowercase a, CA as lowercase b, and AB as lowercase c, we let S equals a plus b plus c over 2, and this is a semi-perimeter of the triangle, so this is half of the perimeter. And now the formula is to prove that the area of triangle ABC is the square root of S minus A, S minus B, and S minus C. So this is a formula for the area of the triangle in terms of its side lengths only, because S is also in terms of the side lengths. So we'll be going through the proof of Heron's formula. If you like to have a go trying to prove the formula yourself, you could go ahead and pause the video and have a go at it before having a look at the solution. Okay, let's have a look at the solution now. So first thing I'll assume is, without loss of generality or using symmetry, we can assume that angles B and C are acute. And the reason why I'll do this, will come up later. So we now let D be the foot of the perpendicular from A to BC. So we set D as this point over here. And the reason I made angles B and C acute is so that D now lies on the side BC and D doesn't lie outside BC. Now we'll label the side length AD equal to H, and we make CD equal to X. So we have X, H over here and X over here. And this means that side DB is equal to A minus X. So it's because CB is A and CD is X, so DB is A minus X. That's over here. Now we'll apply Pythagoras theorem on two different triangles, CAD and ADB. So this is triangle CAD and this is triangle ADB. And this gives us x squared plus h squared equals b squared. So that's using the legs of triangle CAD, x squared plus h squared, and the hypotenuse is b squared. And also on triangle ADB, we have this a minus x squared plus h squared equals c squared. That's the c is the hypotenuse. So then we have these two equations over here. And if we expand the second equation out, the a minus x squared, if we expand it, we get x squared minus 2ax plus a squared, and plus h squared is equal to c squared. Next step I'll do is subtract these two equations over here. So I'll do this x squared plus x squared plus h squared minus this thing over here. And this is supposed to give us b squared minus c squared. And now we see that the h squareds cancel out and the x squareds cancel out as well. So we just end up with 2ax minus a squared equal to b squared minus c squared. And dividing by 2a gives formula for x in terms of the side length. So we have x is equal to a squared plus b squared minus c squared divided by 2a. So now we can substitute this value for x back into this original equation up here. This will allow us to find a formula for h in terms of the side lengths. So we have this expression for x, and then squared plus h squared is equal to b squared. Now if we solve for h squared, we will have this for h squared, so b squared minus this expression. And now we're going to try to expand and simplify this entire expression over here. And we'll use some difference of two squares factorization as well here. So firstly, I've brought it all under a common denominator. So I have 2a all squared here. So you can multiply it by 4a squared in here to get 2ab all squared. Now we have 2ab all squared minus this square number here, and divided by 4a squared. And this is where the difference of two squares comes in, because now we can do 2a minus this thing here and 2ab plus this thing over here. Now we can again, in fact, we can apply difference of two squares again if we set it up correctly. So we can put c squared here and then minus this, and then this gets converted, can be factorized into a plus b all squared, and then minus c squared. And now we have c squared minus, and this is equal to a minus b all squared when factorized. And again, we can apply difference of perfect squares because we have perfect squares here, 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 here. So now we can do c plus a minus b times c minus a plus b times a plus b plus c times a plus b minus c. So now we have four different factors. And now this is where we can use the value of s is equal to a plus b plus c over 2. You see that 2s is equal to a plus b plus c. So we can actually find expressions for each of these values over here. Because, for example, if you do 2 times s minus a, that's the same as subtracting 2a from here. So we have b plus c minus a. Do a similar thing here, and here we get 2 times s minus b is equal to this, and 2 times s minus c is equal to this. And now we see that these factors, these numbers here are the same as this numbers on the numerator. So in fact, we can write h squared is equal to 2 times s minus b times 2 times s minus a times 2s times 2s minus c. That's just substituting all these values up here. And this is looking quite close to Heron's formula now. So this we have 2 times 2 times 2 times 2 is 16 up the numerator, and divided by 4 is 4. We have 4 here. And also we are moving the a squared here to get ah all squared. And now if we take the square root of both sides, we get ah is equal to 2. So the square root of 4 is 2, and 2 times the square root of s minus a, s minus b, s minus c. And finally, we can find the area of the triangle, which is half times base times height. This is half times ah, because you go back to the top, the base was a and the height was h. So half times base times height is a half ah. So then the 2 disappears. So we have the square root of s minus a, s minus b, s minus c. This completes the proof of Heron's formula. Hope you enjoyed this video. Thanks for watching, and I'll see you next time.